Hello friends, I am Fernando Méndez from Mexico. I am Physics student by Facultad de Ciencias UNAM. My project had the title Electronic Properties of Iron, Selenium sub X, Tellurium sub 1 minus X compounds from DFT calculations. This work made in collaboration with Dr. Cecilia Noguez, a pioneer in DFT and computational physics in our university and in our country.
Next, a brief introduction. The growing research of topological materials also increased the interest in iron-based compounds due to the discovery of a topological band inversion on iron selenium sub 0.55, tellurium sub 0.45 predicted through density functional theory (DFT) calculations. This fact and the helical spin Fermi surface of this compound make it an ideal candidate for Majorana bound states MBAs, which were experimentally confirmed later. This fact positioned these compounds like great candidates to research in material science. Since the iron selenium sub 0.55 tellurium sub 0.45 compound was the first material with possibilities of home MBAs in bulk proximity. This due to topological properties which has predicted through DFT calculations. This and its changing behavior with X make it materials with many things for study. Next, a brief description of method utilized for calculations. DFT calculations were performed using a double zeta polarized basis set with a real space grid cutoff of 500 Rydbergs. We employed norm-conserving pseudopotentials and non-local exchange correlation functional to describe van der Waals interactions. Atomic positions were relaxed until force on each atom were less than 10 millielectronvolts over angstrom. The parameters were tested by comparing with previous calculations of non-relaxed iron, selenium sub X, tellurium sub 1 minus X crystals with X equal 1.0, 0.5, and 0, showing excellent agreement. The iron selenium sub X tellurium sub 1 minus X compounds are built by adding tellurium atoms to the iron selenium cell were shown in figure 1a with X equal 1.0 in adequate proportion as exemplified in figure 1b with X equal 0.75. Eventually, we arrive at iron tellurium figure 1c with X equal to 0. The Brillouin one zone and high symmetry points and trajectories are shown in figure 1d. How it was seen, the build of the different systems was realized by doping, adding tellurium atoms in lattice, and if necessary duplicate the unit cell of the limit case iron selenium, like in the systems with X equals 0.75 and X equals 0.25. With the computational details previously described, we have obtained the next results captured in these graphs, which are presenting the electronic band structure in the right hand and the density of states in the left hand. In the graph A, we have a limit case X equal 1.0 and iron selenium compound, while in graph E, the other compound limit case X equal 0.0 and iron selenium compound. This shows a similar energy dispersion on first below one zone, exhibiting a pair of difference like the breaking of degeneration in gamma point in iron tellurium, an increase of localization in states in gamma path by diminishes X. This change can be appreciated gradually in other graphs. In the graph C, show an intermediate case X equals 0.5, a compound with an atom of selenium and an atom of tellurium, for each 2 atoms of iron. In this, observe a change of density of states near Fermi level, and the breaking of degeneration is seen in gamma point. These systems are comparable since the unit cell have the same structure and quantity of atoms, and these were not submitted to duplicate like cases X equals 0.25 and X equals 0.75 in graphs B and D respectively, which are systems built through cell duplication. This can be reflected in folding of bands. This can be seen in the gamma point ligand apparent vanish of gap between states. Another fact to destacate is the contribution of 3D orbitals of iron atoms to density of states, which amplitude dominating over 4p and 5p orbital of selenium and tellurium respectively, especially below Fermi level, which with the more important contribution of 4p and 5p orbitals over Fermi level indicate the existence of empty bands in conduction levels. Finally, the conclusions of our work. Our research has revealed that all iron selenium sub X tellurium sub 1-X compounds are stable within a tetragonal unit cell, with A equal to B less than C, with lattice constants increasing as X diminishes. All iron selenium sub X tellurium sub 1-X show metallic behavior with density of states at Fermi level increasing due to the tellurium atom additions. The presence of 2 different chalcogenides breaks the degeneration of states observed at the high symmetry points when X different to 1, as well as localized states along XR and gamma Z paths. These paths are related to Z direction, where a small interaction between layers is observed, giving rise to the very small band dispersions. Besides the band folding due to the expansion of the unit cell, the presence of the tellurium atoms shows bands that significantly change the density of states as shown in figure F. The density of states is dominated by the iron 3D orbitals with some presence of selenium 4p and tellurium 5p, which are mainly at the conduction bands. However, the flat bands are split because of the introduction of tellurium atoms, contributing to an increase in some peaks very close to Fermi level. Peaks around the Fermi level come closer as tellurium atoms increase their presence. To investigate the superconductivity properties, we will report elsewhere the Fermi surface of these compounds, adding spin orbit coupling effects.